For the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on theories of reaction rates. This will be the first of several lessons on this topic. I am sure you remember in our last lesson how we learned about some factors that affect the reaction rates of chemical reactions. We specifically discussed catalysts, which are substances that, when added to a reaction, affect the rate of that reaction. We learned that while a catalyst affects a chemical reaction, and the catalyst may be affected during that reaction, it is always possible to recover the catalyst in its original form at the end of the reaction. We also learned about the different classifications of catalysts. We learned that they can be positive or negative, which shows whether it slows down or speeds up a reaction. We learned that they can be homogeneous or heterogeneous, which shows us whether the catalyst is in the same physical phase as the reactants. We also learned that catalysts can be biological or non-biological, which shows us whether they are affecting reactions that are either biological or non-biological in nature. Finally, we defined activation energy, which we will take some time to review today. Last class, we discussed factors that affect reaction rates, and in the next few classes, we will talk about two theories used to explain these changes. While both of these theories are very distinct, they are both in agreement with one another. Each theory represents different features of the reaction process. Today, we will focus on one, though. We are going to discuss what the collision theory is and discuss how it can be used to explain changes in reaction rates. Let us get started. Collision theory states that reacting species, such as atoms, molecules, and ions, must first collide before any sort of chemical reaction can take place. This means that these species have to come into contact with one another. It is very much like the game of billiards. When the balls collide in certain ways, points can be gained. However, other collisions that lack power, precision, and angular placement do very little at all to further the game. The rate of reaction is directly affected by how many collisions happen every second. This is referred to as the frequency of collision and is represented in the following equation. The number of collisions during a reaction divided by the number of seconds it takes for a reaction to take place. Students, let us do an activity. Use the equation we just looked at to do the following question. If a reaction has 5,498 collisions and it takes 804 seconds to complete, what is the rate of reaction?
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. Did you figure out the reaction rate? If you said that the rate of reaction is about 7 collisions per second, then you are correct. Let us continue. According to the collision theory, the more collisions that happen within a unit of time, the faster the reaction will take place. However, not all species create a reaction when they collide. Some collisions are called ineffective. Ineffective collisions do not result in a reaction that forms the desired product. Other collisions are called effective, which means that a reaction does take place and the desired product is formed. In order for this type of reaction to happen, the reacting species must be properly aligned with one another at the time of the collision. They also have to collide with enough energy that they rearrange or completely break their bonds. This is known as activation energy. It is the minimum energy needed during a collision for a reaction to take place between the reacting species. Activation energy is written as EA. The alignment or orientation of reacting species can be either linear or bent. Collisions that take place when reacting species are in a linear orientation create faster reactions. Collisions that take place when reacting species are in a bent orientation create slower reactions. Students, draw one of each type of orientation. Then, explain why one orientation is better for faster reactions and the other results in slower reactions.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. The linear orientation creates faster reactions because it has a higher concentration. This means that its spread out particles create more opportunity for collision between other particles per time unit. The bent orientation creates slower reactions because of its lower concentration. This means that its particles will take longer to collide with other particles per unit time. Temperature also has an effect on the amount of energy reacting species will exert. As the temperature of the species increases, so does their energy. If the temperature goes down, the amount of energy they have follows suit. In today's lesson, we talked about the collision theory, which states that reacting species must first collide before any sort of chemical reaction can take place. We looked at how the amount of collisions within a specific unit of time has a direct effect on the reaction rate. We also discussed factors that affect the collision of these species, such as the force and angle at which the collision takes place, the concentration of the orientation of the species colliding, and the temperature of the species colliding. This is all the time we have for our lesson today. Until next time, thank you, teacher. Thank you, students.